So once we've made these gases, we need to get it to the instrument. And does this diagram look okay to everybody?
Kind of Escher-like.
A little bit Escher-like, yeah. I'm going to show one of the interfaces that allows the instrument to get access to these gases. And the point you want to learn about this instrument is the instrument out here has got a hollow glass tube. It's a very low vacuum. The end of this tube is at a very low vacuum. It sits there and it sniffs the whole time. And as the gas passes by, it sniffs it. And that's how it gets its sample. Because this is open to the atmosphere. This is not under vacuum. This is under very strong vacuum. These things actually move around. So this is the universal interface. It's very clever in that you can have a lot of different reference gases. You can dilute them in various degrees. So I've diagrammed those by smaller and bigger tubes. And the same with unknowns. So here's how it works. If you open that valve, the CO2, in this case, can come down. And here's the sniffing part. And the instrument grabs it and analyzes it. And it'll do that the whole time that you're letting CO2 come in. If you turn it off, on the other side, you can have an unknown gas come in. Usually you have too much gas, so you get rid of a bit of it. And then it comes through, and there's another sniffer on this side that allows the instrument to look at the unknown. And this is how these universal interfaces work. Before the advent of this, everything was very manual, very slow. A good day was 10 or 15 samples. Now you can run 100 samples tonight while you guys are listening to me talk. So it really changed things a lot, having these interfaces. If you have a low helium flow, you can actually take one of these capillaries and stuff it up inside another capillary. And you can look at very small samples doing that. So that's called the universal interface. So once we've got gas going into the instrument, it's pretty simple what we do to it. We make some ions, we separate the ions, and we count the ions. And here's how we do that. Here's the infrared or the isotope ratio mass spectrometer. Send a gas in, bombard it with electrons, make some ions, send those ions down a metal tube called a flight tube. When these ions hit the magnetic field, they get deflected. Light ones get pushed further than heavy ones. And at the end, you count them. So it's all pretty simple, at least here. So this is how we separate out isotopic species of a particular gas. And I've used CO2 as an example. With 44, 45, 46, you can see the isotopic species there. And here's how they've separated, with the heavy one being deflected less than the light one. It happens across every gas you do. This is how it does it. The way that we can look at different gases here is, let's say this happened to be nitrogen. Well, that weighs different. It's going to move differently. So we change the magnetic field mostly so that we can still hit the same detectors. That's all done by computer. Now we'll go through the instrument for the three different parts. And the first one is the source. So these are gas instruments. Now we send a gas in, it gets bombarded by electrons. This is like a little hot wire from like a light bulb. Once we've formed this positive ion, just think about that as a little magnet. And what we do is we make that little magnet get inside of a repelling big magnet, and it shoots it out of there. It gets accelerated, goes past some electrical lenses. That's what these guys are. So we can focus it, move it up, down, left, right, and focus it on the detectors at the end. All three parts that I'm showing you upstairs by the conference room where you guys were hanging out most of the afternoon looking at data. There's a plexiglass table with these parts inside of it. You can see what these things look like. My favorite part of the whole instrument is the magnet. It's really cool. So I'm going to show you two different cartoons of the magnet because I like it. So if you take a light ion and you make it go through this magnet, it's going to be deflected and bend. So, you know, obviously we're going to throw the heavy one in, and it's going to do, you know, the same kind of thing. But I like to look at this from the top. So now you're looking down on the magnet, okay? The magnetic field's coming out of the screen headed towards you. And those of you can think back about the right-hand rule. You remember that from physics? Okay, that's what's going on here. Okay, so let's send a heavy ion through, see what happens when it passes through. Well, it bends. And we send a light one through, and it's going to bend a little bit more. But, and this is the only heavy lifting in this whole lecture, is this little equation. And by the way, if you want to see these derivations, you all got one of these books? It's all in there. I suggest you a little light reading tonight. It's all there. Okay, so, but when you look at all the forces on these ions, it all gets kind of summed like that, but that's too much bother this late at night after eating. And it turns out that for any given gas species like CO2, a lot of these are constants. So if you combine those all into a constant, and as Albert said, let's just make it as simple as possible, then the equation reduces down to this, and it basically says the radius is proportional to the mass. Okay, and that derivation is in the book, so you want to see how that all comes about. You can look at it in the lab manual. So just to further it, I wanted to put these fancy little circles on there so you can actually see that one's really bigger than the other one. Okay. The detector arrays are called Faraday Cubs, and their whole purpose is to, I'm going to move on from that one, is to be able to count these ions. And the way they do it is pretty clever. Here's our ion. It comes in, and when it touches the Faraday cup, it gets an electron back. Remember, we knocked one off in the source. That's how we made the ion. Well, when we give it an electron back, we form a little current. And we've, as science kinds of folks, have been really good at measuring current for a long, long time. And so the amount of current is proportional to how much electrons we send back. So you can count kind of how many ions were there. And this is how the systems work.